Yes, you're sharing and we can
Okay.
see it in presentation mode.
Okay, wonderful. Thank you. Um, all right. So thank you, Robert, for the talk about these methodological aspects, about all of these mechanisms behind, and also thank you, Laura, for the invitation today. My part will be much more focused on anecdotal observations on a single HPC system. So this is kind of a lessons learned talk. And not so much a broad overview. But I think it still fits nicely afterwards. And so we are talking about idle power optimization on HPC systems now. And so the first question is, why should we even care about idle power consumption? What do we mean about idle power consumption? So I'm talking about the node granularity. That means not like short phases in an application or single cores being idle. That was more of the aspects of that Robert talked about, like in between optimization of an application itself. But this is more an operational optimization when you consider a full node being idle and being ready to execute a job. Um, so basically, when is this happening? So of course, we are trying to utilize our systems as much as possible. We are trying to increase the scientific output of our systems, but still we have phases in our operation where the nodes cannot do any useful work. This can, of course, be the classical examples before a large job is being executed on the system. There will be gaps in the scheduling. So those gaps can sometimes be backfilled by smaller jobs, but not always. So this is a classical example, but we also have some situations where the node itself is fully functional and working, but there is a maintenance of the file system, so the file system won't work, or maybe the time before the maintenance also has gaps in scheduling because the longer jobs cannot be scheduled anymore. So there are plenty of cases where we have full nodes being idle besides being ready to execute jobs. Now, one little asterisk to say here is that we could use suspend states on these nodes. This has been tried before, but this has not really been applicable to the practice, unfortunately, mainly due to stability concerns. So we are not talking about suspend states in this context. And um, now I would this is a webinar, so it's hard, but maybe you can ask your administrators, or maybe you can the answer in your head. How busy is your HPC system? Is it always 100% busy? Do you know the percentage of time where individual nodes are fully idle? Um, this seems to be sort of an open question, so there are not such great information about that. Now let's go to the system that we are observing here. So this is ZIH, a T-Reston system Barnard that has been in operation since October 23 last year. And so this is sort of a mid-sized systems, I would say, with 630 nodes for CPU only nodes, and dual socket Intel Sapphire Rapids nodes with about 4 petaflops peak performance and file systems. But the interesting aspect here is what happens if this system is idling. So we have 630 nodes here, and let's assume for now that the lifetime of the system will be 8 years. This seems like a stretch, but actually nowadays we've seen more and more systems running longer than expected. So 8 years is not totally unrealistic. And now I'm using a hypothetical idle number of 20%. You can replace it with any other number if you have a better one, and an energy price of 30 cents per kilowatt hour, which is also sort of very fluctuating right now. It's hard to say with energy prices these days. But just to give a roundabout number of what an optimization is worth, and this is absolutely not accurate, but just reducing the idle power by 1 watt for a single node would save us about 2.5 thousand euros, just as a roundabout number. And now the question is, what potential do we have to save power in idle? So let's look about, again, some rough numbers here of a single node of this system, what does it consume in power? So if it is fully utilized and we are using Firestarter as a synthetic application to cause the highest power consumption possible, then one node and all of the cores being active and in turbo mode will cost us about 810 watts. That is a full operation. If we go to just a single core, so we have the same configuration, but one single core is executing the same workload, and we have over 100 idle cores on the whole system, we still use over 55% of the power budget. So we still use over 400 watts here, and this is a relatively high number compared to previous generations. So Sandy Bridge-ish generation, we only saw about 31% power usage of a single core being active, despite having less cores. And next, we can use C states, but only use the C1 state that Robert talked previously on a single core. So basically, all of the cores are sleeping in the deepest C state, but a single core is going into C1. And still, here we consume 308 watt on average. This is actually a relatively noisy figure on a node being measured. So these are 90% quantiles. Just for illustration here. And now what happens if we go in the deepest sleep state and we go down on the average power, but there's still quite a lot of variance here in the measurements. So all of the cores are not executing anything. We have the deepest C states available on all cores, and we have 270 watts. Now this was all with a default frequency setting, which is basically the performance governor allowing turbo mode. And now we can make the same observations with the power save here. And one thing that we see here is that even in the deepest idle states here, we have a frequency dependent power consumption. This is a bit unusual because this was not the case on previous systems, because we actually have mechanisms that the frequency of the cores itself is being reduced when the cores are going into idle, but not this does not seem to be fully applied on this system. But still, so basically the final target that we can reach here is about 174 watts on the node in the power save governor with all the C states enabled. And so this is about 21% of the maximum power. And to compare it again to previous generation on Sandy Bridge systems, we've seen about 10%. So this is much worse in terms of power proportionality. Now, how do we apply this in practice? Oops, why is this black? Okay. So the first step that we had to do, or basically this actually was done by the vendor, when we got the system and had a first look at it, it was consuming the 260 watts power, which corresponds to the C6. Let me point it out, to the C6 state, but with the turbo governor. So we had the turbo governor on, even if the nodes were not executing any jobs. So the first step was a very simple fix to basically have a Slurm epilogue script that sets the frequency to power save. It also enables all idle states, but that is not really relevant because they are unenabled anyway. And this drastically reduces the power consumption when no job is executed on the node. And this is the idle state that we are interested in, the full idle state. And basically, this script with one line of code saves about €250,000 over the lifetime of the system, just by reducing the frequency with no executed jobs. And this was done by the vendor during the acceptance test. They had to do this, but as we can see, this is still not meeting our target idle power consumption here. So we still need to look at why do we have here an increased power consumption and what is keeping the processor alive. Now, there are some tools available to do that, and the first one that we can go to here is the PowerTop tool. You might have used that before. It tells you some interesting summary about the state of the CPU and the package. So on the right here, we see the states of the CPU. We can observe that the cores themselves are mostly in C6. about 90%. Many of them have actually 100% on package 1. But the package C state is pretty bad. We have only 60% of the time spent in the package C state 6. C7 is ignored here for now. And if we add this up, we see that there's actually a significant time where the package itself is fully active. And this goes for both packages symmetrically, again, as the packages influence each other if one package is waking up. Now we can also see what are the, as PowerTop puts it, the top 10 power consumers in terms of the number of events, the wake ups per second that a process or a timer is causing. And this gives us a bit of a fuzzy list here. But we actually see the culprit here, at least one of the culprit already, which is the network code here. But let's go and to look at this problem now from a different angle. We can also look at it through the power consumption, which we measure on this system on different levels. So here we have a node level power measurement of about 6 of the nodes. And the interesting thing that we see here is there are some spikes in the power consumption every 5 minutes. We will come to those spikes in a bit, and there are some other patterns. They are a bit blurry, and what we see here is bands of minimum and maximum power consumption in certain low time intervals. So it's a relatively noisy signal, and we can actually go to a different measurement point to get a better picture here, which is rack level measurements. So these measurements are from the power going to the racks, or at least going to pairs of racks. Therefore, there's some measurements with 2 racks and some with 1 rack. And here the noise of the nodes themselves is averaged out. And we also have a very precise high resolution measurement that actually is 5 measurements per second. And with a very well-defined accuracy. And we see here this 5-minute pattern, but we also see some underlying signal here with 4.5 minutes intervals. And this is perfectly synchronized among all the racks. So all of the nodes and all of the racks have these same patterns. And this also tells us there must be something that's correlated either through time or through global events. And network in this case is a global event. And actually, we can see at this even more fine-grained. So we have, now we are looking, one line here is 1 second apart. And we see these 200 millisecond measurements. It's actually because there are sums of those, there are a little bit more than 200 milliseconds. But we see that even inside 1 second, the power consumption of all racks follows a synchronized pattern. And so this can only happen if you have a common cause for the increased power consumption that's very tightly synchronized. And this is, of course, here the network. And so now we can, in this case, look at the network traffic of one node with package capture and showing it in Wireshark. And we see some global traffic here. We see DHCP messages, and we see ARP messages. So those are network management, network control messages that are broadcast globally to all of the nodes. Looking at also from a different perspective, this is about 40 packets per second on the Ethernet device. So this is another way of investigating this would be the Ethernet device statistics. And if we split this and plot this over time, we actually see here these patterns for the ARP protocol and the DHCP, and they follow, in this case, the ARP follows the same pattern of that we saw in the power consumption. Now, the next thing I did is actually a cross correlation between the package rates of the certain package types and the power consumption. So this is again a confirmation of what we already visually looked at with a certain time intervals of those network traffics. But I'm going to skip over that for time reason and not explain it to detail. I apologize for that. I will go to now to our mitigation or fixing strategy for this. So the first step for the network was to disable the DHCP. and this was actually caused sort of by a bug introduced in the BMC firmware update, where the BMC started. So this is a management controller of each node. Started to continuously send DHCP requests to get an IP address on an interface that's actually not used. And this is a bit weird because the BMC network is supposed to be separated, but it uses the same physical network, and therefore those packages wrongly arrived also at the compute nodes, right? So the management network is supposed to be separate, and the management controller is sending out these control messages, but they arrived at the compute node interface and woke up the compute nodes. Now, when we disabled this and fixed this issue together with the vendor, we saved another few watts, about 6-7 watts per node, and now we can go to another pattern. So this is, I'm jumping a bit around because it's a chronological order. The next thing we did was address this 5-minute interval spikes that we saw previously. They are very simple. This is just a script that runs every 5 minutes to check the node health. This is an extremely inefficient script because it takes 2.5 seconds to check for the node health. And in this 2.5 seconds, as we remember earlier, the node will consume 55% of its full power. So, the mitigation here is just to reduce the interval or increase the interval to 15 minutes, which is a trade-off between the consumption of this script, but still providing sufficient information about the node health status. And the next, again, chronologically, what we did was to disable more network traffic, in this case, the address resolution protocol traffic. This is, again, another network regression. So this is not as it's supposed to be. It's basically a bug. There was a network interface from the management card that was, again, still connected, even though it wasn't supposed to be. And this was causing this noise. And now, from the network people we talked to during this process, it is expected to have some sort of noise for management traffic, for DHCP and ARP and whatnot, in these kind of layer 2 networks, or in common large layer 2 networks. But I would argue that HPC systems are not necessarily a classical layer 2 network. They are fairly static. The devices change only in well-defined process. There's not like a server farm where you have a new server every now and then. And in this case, I think we can argue that in HPC networks, this should not be as much noise. There are certain modern techniques to hide these ARP packages from the nodes. This is actually relatively new network technology like EVPN, to reduce and isolate certain parts of the network to hide them from this global traffic. And we finally tweaked certain timeouts on the core switches. So this was, again, sort of just increasing the interval in which these traffic happens, such that it has not such impact. And with that, we were able to reduce, again, the power consumption here, from these 177 watts down to 172 watts, again, 5 watts. So this was not exactly perfect, but this was the final state after the acceptance. So we see that we are still missing about 12 watt to what actually, we were able to save 12 watt from all of those network and node health control updates. But we still have quite some time in inefficient package C states. So there is certainly potential to improve this, but there were no ways to really do this. So we tried to disable the network manager, which was a daemon running on the nodes that was updating or waking up regularly. Or we tried to disable a flashing cursor, which is actually a pretty weird thing. You have these HPC systems, but still there's a kernel code for a flashing console cursor that is waking up regular intervals. but those changes did not show any measurable impact on the power consumption. Now, I said this is a final state, but this is the final state in basically October when we put the system in production. But now, after 4 months of operation, we actually have a new picture here. We see that we have introduced more noise again. So we added another 6 watt or 4 watts of power per node from certain effects, and we are not yet able to fully distinguish this. So we see new patterns with spikes every 30 seconds. We know that this is a monitoring script providing performance information of the nodes. But we also see some high frequency variations that are again synchronized among the nodes, but this time not caused by a network. And we are still investigating this. And we also see actually more network traffic, but the network traffic in this time does not correlate that well with the patterns we see on the system. And the pictures here we see is actually from this week where we had a file system maintenance. So the compute nodes were running in the full normal state, but the system was inaccessible and unable to execute jobs because of the missing file system. So this is one of the rare opportunities we have where we can investigate the full system at idle. And I want to show why this is important on the last content slide here. If we compare these two pictures here on the top right, we have these measurements from the racks. So where we have all the nodes together measured with a precise measurement and with a high resolution, we see this pattern very well. And on the bottom, we see here, these are the measurements from the compute nodes themselves. So these are just picked randomly 3 nodes, and we have the DC measurements of the full node, and we have the per CPU measurements. And it is so noisy that it's extremely hard to see any pattern here. We do see that there are certain, what might look as an outlier that corresponds to these regular spikes. So the information is there, but it is very hard to extract this information. Only if we actually add all of those values together, then we get a picture that's rather similar to this measurement. So it's not something that happens outside of the nodes in the rack. We know that, but it's not visible if we just have one node to look at. So here really the challenge is, can we get measurements on the nodes, power measurements of the nodes that are as high quality as we have on the racks? This is very challenging because those are not bad measurements. I don't want to say that these power measurements on the nodes are bad in any way. They are 1 sample per second updated, which is a relatively high rate compared to many other systems. But still, we see that for this use case, it's actually not enough. And so the question here to pose is, how can we investigate these issues without taking large parts of the systems, like exactly 1 rack or something like that, out of the system operation? And this is sort of an open question. And now we come to the final thoughts. So the big thing about idle power optimization is that if you go idle, if you don't have any work to do, you must make sure that the system is really fully idle, that there's nothing interrupting the system and waking it up. And HPC is actually special in that case because in many, like if you have a web server and if you say the web server is idle, it typically means that you only have very few requests, because it's in the night and no one's visiting your website. You have very few requests, but you do still have requests. But on an HPC system, if there's no job being scheduled on an HPC system, the work that is being done, the effective work that's being done is actually really zero. It's not 0.5%, it's 0%. And in that case, HPC is special. And we must make sure that not even a single core is active, or not even a single core is barely active, or woken up 40 times a second, because this is very expensive to wake up a single core 40 times per second. And another important thing to take away here is that idle power now depends on the frequency. At least on this Intel generation, we can all hope that this will go back again, and that we have frequency independent idle consumption, but it's not sure that we will get this. I found very little public information. Some people say they all do idle power optimization if you ask them, but no one seems to deem it, very interesting or publishable. But I think it's actually relatively important. It's so important that it should be part of your procurements or your contracts, but also part of your operation, because regressions on this is extremely likely. So we've seen regressions only after a few months of operation. We've seen that during the installation phase, the regressions with the BMC updates that caused the DHCP requests were happening. And now the challenge here is really that monitoring this during the operation is much harder than during the acceptance, but we want to make sure that we don't have a great idle power consumption right after acceptance, but then we run the system 8 years with a bad configuration. This should be avoided somehow. And with that, I hope I'm